to the second PhD school session. I think we have 3 talks. We have about an hour, and I will leave the first speaker to come up and present. So there is already what is happening here. So Rui Xiui is going. Jesus. Alex, we have already a small technical issue. You have to fix the timer because, well, as there is no board, I would have said to him, please write on the board.
I thought it would be fine.
Thank you.
With all the slides?
So, Rui is going to speak about a study on quantum distance-based machine learning algorithm applied to the TSP problem. The Euclidean one.
Yeah.
So,
Can I use this one?
I think, yes.
So, I just use this one. Yeah. So many thanks for coming to this presentation. And my name is Rui Xu. I come from UTBM. And today I'm very happy to share with you this presentation. It's about a study of quantum distance-based machine learning algorithm applied for the Euclidean TSP. So here is the outline for this presentation. I will focus on 5 parts. For the first part, I will introduce the quantum optimization algorithm and the state of art for this subject. And then I will give a brief introduction for the self-organizing map method for the TSP. And here includes the problem set and the visualization for this method. And for the 3 part, it will be a quantum enhanced version for the sum for TSP. So then I will introduce the experimental results and the observations. At last, the future directions and challenges and opportunities will be introduced. So let's get started. So for the covering salesman problem or the TSP, it is a well-known classical NP-hard problem. And because of its computational capacity, solving the large instance efficiently is extremely challenging. So to improve the scalability and the speed, the parallel meta-heuristic approaches has been used widely. For example, the GPU accelerate algorithm, it has significantly improved the speed and by exploiting the parallelism. And recently, the quantum computing has introduced a new paradigm for optimization problems. And with the QPU accelerate algorithm, there is a potential that for further speed up for the NP-hard problem like TSP. And now the quantum computing can offer some theoretic advantages for solving some certain optimization problems. For example, the Grover algorithm can give a quadratic speed up, and the Shor's algorithm can provide exponential speed up for factoring. And all this thanks to the quantum parallelism that n qubit can represent 2 to n states at once. And here is some representative quantum optimization algorithm, the QAOA, and the quantum annealing, which is implemented by the D-Wave, and the variational quantum algorithm. It can optimize the cost function using the parameterized quantum circuit. So although the quantum computing can offer great potential, but since we are in the noisy intermediate scalar quantum era, we have some limitations. For example, the limited number of qubits and high error rates and short decoherence time. So the hybrid quantum classical method was proposed. It combines the classical module and the quantum module. In the classical module, we can do the data processing and the parameters update. And for the quantum module, we will do the data encoding, implement the quantum circuit for specific problem and return measurement results. And it will create a loop that the quantum and classical components can work together so that we can make the most of both technology. And then we come to our talk, the self-organizing map for the Euclidean TSP. So there is two challenges for this method for the Euclidean TSP. The first one is for the best matching unit search in the sum process. It's very computational expensive because each time we need to compute the Euclidean distance. And also for the Euclidean TSP, it depends on unnormalized city coordinates, and many quantum machine learning methods assume the united normalized data. And now here are some recent distance-based quantum machine learning approach. The quantum KNN, it can estimate the Euclidean distance via the quantum interference, and the quantum k-means, it can provide quantum parallelism to speed up the k-means clusters. And so our research project is to integrate the quantum part in the best matching unit search process. And until now, no previous work has done before, so we want to fill in the gap. So for the traveling salesman problem, which is motivated to seek the shortest route that visiting a set of cities exactly once, and for its Euclidean version, that each city CI is defined by its coordinates, the CI equals xi, yi, and the total length is denoted by this formula, where pi is a permutation of the cities and the distance is computed by the Euclidean norm. So then we coming to the sum for TSP. So we start with the initialization begin with a set of narrows and with their weight vectors wj randomly, and then we go into the training process. During the training loop for each city and for each iteration, we will do the following key steps. The first step is the BMU search, that we will find a weight wj which is closest to the input city xi. And after we find this BMU, we will do a weight update. We update the BMU and its neighboring neurons based on a neighborhood function. The neighborhood function usually is Gaussian. And after the iteration of convergence, we will extract a tour that by connecting all the neurons in the final position, and it will form a route that can approximate to the optimal TSP. And here is the example of a basic iteration for the different learning rate for and neighborhood size. That for the figure A, there is a point for the input city, and the straight line is the nearest, and after during one iteration, the nearest will get close to the input city. And for this method, it's very straightforward to code and easy to test. So it's very simple to implement it, and it is based on the unsupervised learning, and there is no need for the label data, and it's very intuitive visualization, easy to understand. So we come to a GIF that shows the process of the sum for TSP. So we start with a blue ring, and the ring will get close to all the cities and form approximate optimal TSP. Then we come to the quantum version for the sum for TSP. So the challenges for the classical sum for PSP is that we need to do m times Euclidean distance evaluation per input city, and when the numbers of the narrows is very large, it will become a bottleneck in some large scale self-organizing map problems. So we can choose the quantum for alternative. We can perform the distance comparison in the quantum superposition, and for example, using the quantum interference and amplitude encoding to estimate the similarity, and for example, to use the quantum machine learning tools, the QK-means and the QKNN to find the BMU. So the first method is to compute the Euclidean distance between one input city and one single neuron using one quantum circuit. It will have very simple circuit structure and very feasible for the current NISQ device, but it still needs m execution per input sample, and it's very similar to the classical sum for TSP. And the second method, we do the improvements to compare all the narrows in a single quantum execution using the superposition, that we put the input city and the narrows in one quantum circuit. And it can reduce the circuit execution from m to 1, and it can scale better with increasing narrow count. But it also required many shots due to the sampling noisy. And another BMU search strategies is based on the quantum KNN. We use the extended filter vectors and the amplitude encoding. We want to estimate the inner products to estimate the Euclidean distance. And this method can achieve high accuracy in ideally simulation, but for the sampling-based execution, it will suffer from high variance without a large short counts. So here is the quantum secret for the QK means we call it QSUM, and this reuse the quantum machine learning application of QK and the QK means by using the amplitude encoding and interference measurement, we can quickly get the similarity of the distance. And for the result for the experimental, we test it on the TSP lib. So first we test on the instance of Berlin 52. For the first one is the result of the classical sum, and the next four results is based on the QKNN stack vector, the QKNN local simulations, and also the two method of QK-means. And we can see that for the stack vector, it can achieve almost the same results with the classical sum. And but for the sampling-based method, for example, the QK-means may produce detours due to the measurement noise. And we also test it on different TSP instance on the different method, and we calculate the gap, and here is a form for it. So for the, as I told before, for the stack vector method, it can get a good result, but for the sampling-based method, they will have, they are very time-consuming, and even over 1 hour for the BL127. So, and with the instance size increase, the dips and the gates counts increase significantly. And we are trying to try another method is the QNMK, means that we encode all the cities and all the narrows in one quantum circuit, and this may offer some promising theoretic benefits. For the complexity of the QSUM, it was the QRAM encoding plus the complexity of circuit depends and the measurements. And for the classical complexity of sum for TSP, it's order of MND. And if we discarding the QRAM encoding in dimension D, we could have a polynomial speed up. But this method haven't been implemented because of long simulation time. And for the next direction, we will continue to enhance the method, the QSUM for TSP. We want to incorporate more expressive quantum circuits, for example, using the swap test for the unnormalized Euclidean distance calculation, and even explore the Glover-based search for efficient BMU selection. And there is another possibility for using the real quantum hardware at the NISQ error, and to make good use of the quantum computing and its mathematical foundation. And it maybe make a return to the quantum-inspired classical algorithm. And we propose that we think that the tensor networks maybe help us to better design the quantum circuit, and it may provide insights in the